Yes, thanks, Karin, for the invitation and the nice introduction. And yeah, I'm happy to listen to all these very interesting talks. I'll give a short report on some joint work with my postdoc Özgür Esentepe, who is also somewhere in the audience. Um, so uh, we start. So I hope this is all readable. I'll go through that quickly. So we start with the so-called A infinity singularity. So this is just like a nice commutative ring. So you take like polynomial ring in two variables modeled by x squared, and then this gives you a curve. So if you look at spec R, this gives you the so-called A infinity curve singularity. So like AN, and then in some sense, you can see that as a limit of AN. And then a few years ago, in joint work with Jenny August, Mandy Cheung, Zira Gratz, and Schroll, so lots of people, this was the WinR2 project. We looked at a category of modules over this, namely maximal Cohen-Macaulay modules with a certain Z grading, where you have like this grading where X has 1 and Y has -1. Was what you usually don't want, that you have like your degree 0 part is not the field. But we looked at this and we found that this has actually a really nice structure, namely the structure of a cluster category. So we called it C2. And this has, so this is, first of all, it's a Frobenius category, and it has the cluster structure of type GR2 infinity. So Grassmannians in like planes in an infinite dimensional vector space. So there is a way to make sense of this. And in particular, you can see that the generically free indecomposable objects in this category C2, they're really in bijection to the Plicker coordinates. So we're now there so the index is not by finite pairs of numbers, so you can take any integers as indices, and you still have Plicker relations. And then you also get the bijections to finite arcs in an infinity-gon. And so just that it's clear what I mean with an infinity-gon. So we can visualize this on a circle, which the marked points are indexed by the integers, and we have one accumulation point. Then one can also see that the cluster tilting subcategories of the C2, they correspond to fountain triangulations of this completed infinity-gon. And then here I put that, so there is like a lot of related work that I'm not citing everybody, apologizing for that, but in particular Paquette Yildirim, building on work of Holman Jorgensen and also Igusa Todorov. And one thing that Paquette and Yildirim did, they constructed a cluster character on their category, which is a triangulated category and which is equivalent to the stable category of RSE2. And so here I wrote down the formula for the cluster character. So I'm not explaining all of this, but what is important here is that the sum goes here over all classes in the Grothendieck group of this C2. And so this is very big. So this is actually the integers. And so this sum might be infinite. So we get like a power series, but each term is still finite. So you get a well-defined power series here. So now coming back to the category C2, so together with Özgür, the first thing we do is we show that actually this cluster character of Paquette Yildirim also works in the Frobenius case, so on the full category. So this means you also have the projective injective objects in there. And then also if you analyze the cluster character more, so then you see that you will have a finite sum in this expression here, if and only if the arc corresponding to the module M crosses only finitely many arcs of the fountain. So maybe I think I've prepared that. Let's see if it works. So a cluster tilting subcategory corresponds to a fountain triangulation. And then if you cross only finitely many arcs of the fountain, so meaning like you have an arc that's somewhere on one side, then, well, you get something finite. But the problem is if you want to compute this cluster character for something that's like crossing infinitely many arcs, and then you will get an infinite expression. And so now we come to the next part, to the friezes. So here is like just a slide to see what's in the n-gon to remind you. And so here I have just an example. So if you have a triangulation of a finite end of a finite polygon, then you can associate a Conway-Coxeter frieze to it by like counting how many triangles are incident to each of the marked points. And this gives you the first row of the frieze. And then you have this determinantal relation to get some other numbers in the frieze. And then it's also well known that you can get this from representation theory. And this is like this like grayish part here, and where it's like explained how to do that. Namely, you can go from the triangulation, you can go to the cluster algebra, so the Grassmannian cluster algebra, and from this you can go to the Grassmannian cluster category. So this is the Jensen-King-Su category. And then, so if you are in the category, then you can apply the CC map. And then if you evaluate the cluster to 1, you get all these numbers in the frieze. And in particular, you take the AR quiver, do this evaluation here, and you get precisely the frieze up here. And so now the question is, well, what happens if we do that for the infinite case? And so we can now do this. So we have a cluster character from the Paquette Yildirim. And so we can also evaluate at all the indecomposable objects from the fountain like to 1. And we have already seen we get like an integer. This is only a finite sum if and only if we don't cross the fountain. And if we cross the fountain, then, well, we would get infinite. But then if you like draw this in the frieze, then you see that, well, all these values down here, this would be where you have infinite. And if you want to complete the frieze, you will run into trouble. So we get these like what we call half friezes. So you can just go to the fountain, but not anywhere further. And here you get still some nice numbers. And so you have, so this is how we like obtain friezes from fountain triangulations. And then, yeah, you might ask, what has this to do with Penrose tilings? And so this is the last part. So now we need some special, what's called a special right fountain. So not to every fountain, one can associate a sequence of ones and zeros, which no consecutive ones. So maybe I'll draw again what means special fountain. So I have my fountain here, and special means precisely not that case. Namely, special means I do not have two no two arcs are like an ending in two consecutive integers. So I would need something here. This would be allowed. And this gives me a sequence of ones and zeros with no consecutive ones. And then it is well known that from this sequences of zeros and ones with non-consecutive ones, you get Penrose tilings, and then there's this what's called tail equivalence. So if they like are the same up to finitely many entries, then they are like in bijection to Penrose tilings modulo isometries. And so we can now relate this to these like right half friezes. And so we can say like from each fountain triangulation, we can get a right half frieze. And yeah, and so so here, this is not a bijection because this sequence of ones and zeros only it only tells you like where the arcs in the fountain are, and there can be like stuff in between. So this part here is not a bijection, but we do get friezes from Penrose tilings. And I think that is all I wanted to say.